In this video, we're going to talk about the sine law, cosine law, and we're going to take up the ambiguous case of the sine law. Let's start with the cosine law. Cosine law is used in two cases. When you have a triangle that's a non-right angle triangle, and you know an angle between the two sides and the two sides. So we have a contained angle and the two sides. Another case when we use cosine law is when we are trying to determine at least one angle when we know all three sides. So in case one, we're trying to determine the length of the side opposite the angle, and in case number two, we're trying to determine the measure of one of the angles. So the formula for the cosine law is based on the Pythagorean theorem, slightly changed. Let's look at it. So for example, I have a triangle that we label ABC, and the side length are labeled as lowercase letters opposite the corresponding angle. So A, B, and C. And if I'm trying to solve for C, C will be on the outside squared, then it equals to A squared plus B squared minus 2AB times cosine of the angle that corresponds to the side that you're solving for. If I'm trying to solve for A, then I'll have A squared equals C squared plus B squared minus 2CB times cosine A. And if I'm trying to solve for B, then it's B squared equals A squared plus C squared minus 2AC cos B. And once you know the values, you just substitute them into the formula and try to solve. When we're solving for an angle, then we have to isolate for it. So from the first equation, cos C will equal to C squared minus A squared minus B squared over negative 2AB. Remember that when you're solving for an angle, the last step will be finding the inverse cosine of the given ratio, because you will be looking for the degree measure, not the ratio of cosine. Then if I wanted to find cos A, it would be A squared minus C squared minus B squared over negative 2CB or BC, and then cos B is equal to B squared minus A squared minus C squared over negative 2AC. Let's see how we can apply the cosine law to a problem. The sides of a triangle are 4, 11, and 8 centimeters. Determine the angles in the triangle, round to the nearest tenth of a degree. So here is the diagram. It's important to label your angles and sides so that you don't confuse what is what in the formula, because it's important that the angle that you solve for corresponds to a specific side. So here I'm solving for angle A first. So I'll do cos A is equal to A squared minus C squared minus B squared over negative 2BC. Now we're substituting the values. Cos A is equal to 4 squared subtract 11 squared subtract 8 squared over negative 2 times 11 times 8. The order doesn't matter when it's multiplication. All right, let's evaluate this. Cos A is equal to 0.9602. And then now we need to still determine the angle. So A equals cos inverse of 0.9602. This is angle A. So angle A is equal to 16.2 degrees. The question is asking us to determine the angles in the triangle, not just one angle. So we need to continue and still find angle B and angle C. For angle B, the formula will look the following way. Cos B equals B squared minus A squared minus C squared minus 2AC. Let's substitute the values. Cos B equals B squared is 8 squared minus A squared minus C squared over negative 2 times 4 times 11. Let's evaluate what this equals to. Cos B equals 0.8295. Since we're not looking for cosine ratio, but for the angle measure, we're going to continue with angle B equals cos inverse of 0.8295. So angle B is equal to 34 degrees. Now that we know two interior angles within the triangle, we can use the interior angle sum theorem for the triangles that tells us that the sum of all interior angles inside the triangle is equal to 180 degrees. Therefore, from this theorem, we can determine the value of C, and angle C will equal 180 subtract the sum of the other two angles. So angle C is equal to 129.8 degrees. Our diagram does not really match what we have found because we did not really know what the angles would look like. But if I were to redraw my diagram based on the angles that I have now, it would look something like this. So this would be my angle A, this would be my angle B, they're both acute angles, and angle C is an obtuse angle right here. Now let's talk about sine law. Sine law is used in situations when cosine law is not used, mostly when we have pairs of opposites, a side and an angle and a side and an angle that are opposite to each other, and we're trying to determine one of the missing values. For example, if I have a triangle and I label it A, B, and C, and the corresponding sides, of course, and say I know this angle and this side, and then I'm also given this side, but I'm trying to determine angle C. We don't know what it is. So I have two pairs of corresponding sides and angles, one of which is not known. So that's what I'm trying to find when I use sine law. For example, I can say that sine of angle A to its side length is equal to sine of angle B to its side length. The ratios will be equal and I can solve a proportion. I can also say that any one of those ratios is equal to sine C of C. We normally don't use 3 ratios at once. We use the proportion of the 2, A and B, or B and C, or A and C, whichever one works for us in a particular situation. Sometimes there is a bit of a problem with the sine law that creates an ambiguous case. For example, we're given the measurements and we're given the angle and 2 side lengths, and we're being asked to determine another angle. However, sometimes we need to look and determine first whether those measurements can even form a triangle, or they can form 2 different triangles with 2 different angles, one of which could be acute and the other one could be obtuse. Let's see what that means. Say I have a situation like this in number 1, where I have an angle A, side B, and side A, and a height h. You can clearly see from here that side A is shorter than side B, and it is shorter than the height of the possible triangle. When that happens, there is no triangle formed. So I always need to check, given the 2 side length and an angle, when I'm trying to solve for another angle, whether the dimensions even form a triangle. So I would have to determine the height and see if the opposite side, A, is shorter than the height. Then in situation like this, there will be no triangle. In case number 2, A is longer than B and longer than H, with an acute angle A on the other side. In a situation like this, we have only one possible triangle. In case 3, you can see that A is longer than the height but shorter than the B side. In that situation, when A is an acute angle, you could have 2 possibilities for triangles. The first triangle could be this one, and the second triangle could be this one, and the angle at the base would either be an obtuse angle or an acute angle. So when that is happening, when A has a length that is between the height and the B side here, then you end up with 2 possible triangles. In number 4, the angle A is obtuse, and if side A is shorter than B and it may be equal to B, in both cases there will be no triangle formed. So whether A is shorter than B or equal to B, there will be no triangle. When angle A is obtuse and A is longer than B, there will be one triangle formed. Now let's solve this triangle. To solve a triangle means to find all missing dimensions within the triangle and all the missing measures. So here we need to find the measure of angle C, and we need to find both side C and side A. In order to find the angle C, we can use the interior angle sum theorem for the triangle. So angle C is equal to 180 subtract 52.5 degrees plus 73.4 degrees. So angle C is equal to 54.1 degrees. Next, We can use sine law in order to determine the missing side length. We have the two opposites here, A, and we have two known opposites, this and this, B and B. So I'm going to say that sine B over B is equal to sine A over A. And that is sine of 73.4 degrees over 36.6 centimeters is equal to sine of 52.5 degrees over A. Given this equation, I'm going to be solving for A. A is equal to 36.6 times sine 52.5 degrees, cross multiply, and divided by sine 73.4. So A equals 30.3 centimeters. Now we can repeat the same process to determine the value of the side C. So we have the angle C that we have found, and we can use A and A now in order to determine the side length C using the sine law again. So sine of angle A over side length A, sine of angle C over side length C. So sine of 52.5 degrees over 30.3 centimeters equals sine of 54.1 degrees over the C side length. Now from here, C will equal, we're cross multiplying, 30.3 times sine 54.1 degrees over sine 52.5. So C equals 30.9 centimeters. Therefore, angle C is equal to 54.1 degree. Side A is equal to 30.3 centimeters. Side C is equal to 30.9 centimeters. Now let's practice a little bit of an ambiguous case. How many triangles can be formed given the following dimensions? So we have angle B, and it is 61 degrees right here. It's an acute angle. Side B is 32. A is 35. So side A will come from here. This is equal to 35. And it goes up here. And then there is a side B that is shorter than A. B is potentially equal to the height of the triangle. And in order for us to determine whether it is, we need to determine the length of the height. So that we can determine the length of the height, we need to use the trig ratio for the right angle triangle. So within the right angle triangle of the angle B, side A, and side H, we can use the ratio of sine in order to determine the side length of H. So sine of 61 degrees is equal to opposite over hypotenuse. So from here, H is equal to sine 61 degrees times 35. H is equal to 30.6 meters. So here we can see that side B is shorter than A, but longer than H. So B is greater than H, but less than A. Therefore, there is a possibility of two triangles here. So we can have this. We could have a triangle that looks like this, and we could have a triangle that looks like that. And we could have two possible angles, one here and one here that we would be solving for. So triangle number one would be this one. And triangle number two would be this one, this whole thing, this big one triangle. That happens when B is greater than H but less than A.